sort of definition of a category of Berkovich analytic spaces. Brian will be doing that in his last couple of lectures. I will just be focusing still on examples. So first of all, I wanted to correct something from last time. So there was some sort of error introduced by having doing cutting and pasting from something which I previously wrote, which had a mistake, which was pasted from something else. I can't quite track where this originally happened, but in any case, I said this path metric on Berkovich hyperbolic space was ultrametric, and that's not true. It's just a regular metric, Archimedean metric. But let me just recall the definition, since I said that, and it might have confused some of you. So you'll recall the points of the Berkovich affine line corresponded to nested sequences of disks. And we categorized them up to some equivalence relation. We categorized them into 4 types. And the type 4 were these funny points where you had nested chains with empty intersection. And forget about those for a moment. Now, Berkovich hyperbolic space is where you throw out the points of type 1 over this complete algebraically closed field. And once you throw out the points of type 1, the classical points, you're left with all the new Berkovich points. So hyperbolic space is all these new points, which you can think of as just corresponding to physical disks, if we forget about these type 4 ones for the moment. And so how do you measure the distance between 2 disks in this path metric? So it's actually very simple. You just take, you have one disk, you have another disk. You take the smallest disk containing both of them, and that's well defined, and then call the radius of that capital R. It's just the distance between A and B if these 2 disks are disjoint, and otherwise it's the maximum of the 2 radii if one disk is contained in the other. And so the path metric is just given by the distance between the corresponding points of Berkovich space is just the log of capital R over little r plus the log of capital R over little s. So you go up from here to this big disk and back down to here. And each of these 2 paths has a length equal to the log of the ratio of the radii. And if one disk is contained in the other, it's just literally the log of the ratio of the radii. You just have one term. And so that actually defines a metric on this hyperbolic space. And you could extend it to the type 1 points, but then it would be singular. You'd have those type 1 points are infinitely far away because they have radius 0. Anyway, so this is a metric. Now, the ultrametric I was thinking about when I said that is this canonical distance, which is related but different. So the thing that's in ultrametric is the canonical distance. That, you'll recall, was the following. Again, you have 2 disks. You have the smallest disk containing both, which I called the least upper bound. And the canonical distance relative to infinity, so this is really should be thought of as something that's canonical on affine space, but not on P1, where you could sort of change coordinates around, is the canonical distance between these 2 disks is just capital R, the radius or diameter of the smallest disk containing both of them. So this actually extends the usual distance on K, because if you just sort of think of these as radius 0, then of diameter 0 disks, just a point A and a point B, then the smallest disk containing both, its radius or diameter will be the absolute value of A minus B. And so this is a way of extending to Berkovich space the notion of the distance between 2 points in affine space in K. And this is an ultrametric, except it's not actually a metric because the distance from a type 2 point to itself, for example, is positive. More generally, any point that's not of type 1, the canonical distance to itself is the diameter, and that's strictly positive. So it's not really a metric. Okay, so that was just sort of clarification and review, and now I want to begin. Let's see if I can do this. Oh, screensaver. Got it. Okay. All right, so now we'll begin with lecture 2. So the first thing I want to do is give an alternate construction of the Berkovich projective line that's somewhat more natural than the previous one that I gave. Then we'll see how to view this Berkovich projective line as some kind of inverse limit of finite trees, which I alluded to last time. And then I will give a more general definition of a Berkovich analytic space associated to a normed ring, which is sort of how you take the aphanoid rigid analytic theory and embed it inside the Berkovich theory. But actually, this makes sense for more than just aphanoid algebras. You can sort of take any normed ring, associate a Berkovich space to it. So in particular, it makes sense for just the ring Z of integers. There's some corresponding Berkovich space. And I think it's quite instructive to spend a bit of time exploring the structure of that space, even though perhaps not as useful as the other things I'll be talking about in practice. It's very striking what happens with this space. It's a great example to keep in mind. And then I'll briefly discuss sort of global Berkovich spaces and their topological structure, but I won't get into the issue of how you glue these things together to give global spaces because it's a bit subtle, and I believe Brian will be addressing this. So I will just make some comments, but not give formal definitions. And as in the previous talk, I'll remind you that K is an algebraically closed field complete with respect to a non-trivial, non-Archimedean absolute value. This is just to make life simpler. Okay, so recall that this fundamental notion out of which we construct Berkovich spaces is a multiplicative semi-norm. So a multiplicative semi-norm on some ring A is a non-negative real-valued function satisfying these axioms. So the first one is the absolute value of 0 is 0, absolute value 1 is 1. Second is it's multiplicative. Third is it satisfies the triangle inequality. It's called non-Archimedean if it satisfies a stronger version of the triangle inequality, the ultrametric inequality. And recall that as a set, we defined the Berkovich affine line to be all multiplicative semi-norms on this polynomial ring, which extend the usual absolute value on K. Now this is somehow a direct construction of the Berkovich affine line. One could also give a direct construction of the Berkovich unit disk by looking at multiplicative semi-norms on the Tate algebra in one variable, and then sort of taking an increasing union of balls, as Brian did this morning, and getting some sort of admissible covering of A1 Berk and gluing these together. But actually, there's this nice direct way to construct A1 by just considering the polynomial ring. And it's a not 100% trivial exercise to see that these two definitions agree. And the topology on the Berkovich affine line we defined last time to be the weakest one, which makes these maps x goes to absolute value of f sub x continuous for all f. So you fix a polynomial, and you require that taking the absolute value of that polynomial at some point should be a continuous map. And here was our picture of the Berkovich projective line, rather incomplete because the branching is much worse than I've shown here. But you'll remember there was this distinguished point called the Gauss point, which lies along the path, the unique path from 0 to infinity. We discussed the tangent space at this point, and more generally at any point of type 2, the branches coming out look like P1 of the residue field. And you have branching at a dense set of points along this edge. The branching, where you have branching corresponds to the value group of K, and the different branches that come out correspond to the residue field of K. And so it depends what my field K is, exactly how complicated this picture looks. Now, we defined the Berkovich projective line as the one-point compactification of A1 Berk. But that's a rather hard definition to work with in practice. For example, if I have a rational map from P1 to itself, I would want to know that it induces a morphism from the Berkovich projective line to itself, because this construction is supposed to be functorial. But if you just define it as the one-point compactification by adding this point at infinity, and you have a rational function with poles, it's not completely obvious how to naturally get things to extend. So let me give you a definition that makes the functoriality more evident. And this would be analogous to the Proj construction in algebraic geometry. And this can be done more generally, but I'll just do it for the case of P1 and leave it up to your imagination how to generalize this sort of thing. So this is a crutch by which I can get away without discussing gluing at all, because I'll give you some kind of Proj construction that automatically takes into account the gluing data. So we're going to look at homogeneous seminorms. So let S be the set of multiplicative seminorms on the two-variable polynomial ring kxy, which extend the absolute value in k, and which are not identically 0 on the maximal ideal. And so this is sort of like looking when you have to consider the irrelevant ideal in algebraic geometry as some special ideal. It's quite analogous. And well, these seminorms are automatically non-Archimedean, since the absolute value on k is non-Archimedean. And so you can check that this condition, that the seminorm doesn't vanish on the maximal ideal, is the same as saying that one of absolute value x or absolute value y has to be non-zero. So this will be like the condition that in projective space, both coordinates are not allowed to be 0. And so we'll put an equivalence relation on this set of multiplicative seminorms, these multiplicative seminorms on the two-variable polynomial ring, by declaring that two such seminorms are equivalent if there's a positive constant, so that if G is homogeneous of degree D, then the first norm should be the second norm times c to the d. So they scale in some evident manner with respect to homogeneous polynomials. So under this equivalence relation, well, now we can define P1 Berk as a set to be the equivalence classes of these multiplicative seminorms with respect to this equivalence relation right here. And it's easily checked that this agrees with the previous definition of P1 Berk, but this is somehow more natural. And so the point infinity, I mean, we've already sort of chosen these coordinates x and y, so I'll make a choice that the point infinity will be the equivalence class of the seminorm defined by evaluating at 1, 0. And you see that more generally, if I have a point in P1 of k, I can write it in homogeneous coordinates as AB, and then I can evaluate this a homogeneous polynomial g at a comma b and take the absolute value, and that gives me a multiplicative seminorm. But if I change coordinates, if I use different homogeneous coordinates, then this would get scaled by some power by c to the d. If I multiply a and b both by some constant c, this would get rescaled by, well, the absolute value of that to the d. And so up to equivalence, this is well defined. So given a projected point, we get a well-defined equivalence class of seminorms. And that's the idea here. So you see how P1 of k embeds naturally into the Berkovich projective line. And the topology, well, I can't just say that the map that sends a point to the absolute, that sends, a point to the absolute value of some homogeneous polynomial. Brian? Right.
So in the evaluation example, you said what to evaluate at a homogeneous element. So how do you define it on a non-homogeneous element?
Right. So the question is, I defined well, you can just so the equivalence relation only depends on what happens on homogeneous things. So I mean, I can just pick a representative and evaluate it there. And if I pick a different representative on the homogeneous things, they'll be equivalent. So those two norms, by definition, are equivalent. It really only matters what happens on the homogeneous polynomials. So a seminorm, just to define the topology, since evaluating at a point is not actually well defined, it's only defined up to equivalence, we can find a normalized semi-norm in each equivalence class. So a semi-norm will be normalized if the max of the absolute value x and absolute value y is 1. And then within each equivalence class, we'll have some unique normalized semi-norm. And we can, I'll denote this by absolute value star, the normalized semi-norm. And so you could just take, for a homogeneous polynomial g, you can take this to be the definition of the normalized semi-norm. You just divide out by the max of absolute value x and absolute value y to the d for whenever g is homogeneous of degree d. And now this is something that you can, that's a well-defined real number now, so you can say that the topology is the weakest one so that z goes to absolute value g star z is continuous for all g. And this will be the, if you unwind the definitions, this is the same topology that I did before. Just cover P1 by some affine coordinates, and you can check it locally that it agrees with the previous definition. Anyway, I just wanted to present this as an idea for how to give an alternate construction of the analytification of a projective variety that's projective scheme that's somehow more less dependent on gluing and choosing coordinates and such. So the topology, this topology agrees with the previous one that I defined. P1 of k and the complement of P1 of k are both dense in this topology. And now it's fairly clear that if I have, say, a rational map, a morphism from P1 of k, from P1 to P1, defined over k, then the induced map on k-valued points extends to a continuous map on Berkovich space. So how does that work? For example, you write your rational function phi in homogeneous coordinates as sort of f1 of xy over f2 of xy. So you just choose some lifting of the numerator and denominator to homogeneous polynomials. And then you define the semi-norm corresponding to phi of z is you just take, compose with f1 and f2. And so this is, the right-hand side is independent of the lifting of f because it will just rescale in the appropriate way. And you can check that these can't both be 0, basically because I chose f1 and f2 to have no common zeros. And if you interpret that in terms of the resultant, then it's not hard to check that these aren't both 0. And so you actually get a well-defined map, which from the definitions is continuous. So the map from, an algebraic map from P1 to P1 extends to a continuous map from Berkovich space to itself. And this is just one concrete example of general functoriality of this construction, that you can take an algebraic variety or more generally a suitable rigid analytic space and get a Berkovich analytic space associated to that, which is functorial. And actually, there's many nice properties hold for this induced map. So for example, this map on Berkovich space is an open surjective mapping. And every point z has at most d, the degree of the map pre-images. So on the level of topological spaces, it really behaves a lot like the analog, for the Riemann sphere. A rational map over C will induce a map from the Riemann sphere to itself with these properties. And the same is true in the Berkovich context. And it respects the type of points. So points of type tau go to points of type tau under such a map. And so in particular, hyperbolic space is preserved by the action of a rational map. And you can see this by looking at the residue fields, which I haven't defined. But this is not hard to check. And in particular, the group PGL2K of Mobius transformations acts naturally on Berkovich projective line, and it acts via automorphisms on hyperbolic space, but even better, it acts via isometries with respect to this path metric. So the metric rho that I recalled at the beginning is invariant under the action of PGL2K. And you could ask about a more general rational map from P1 to P1. What happens to this path metric? It's invariant under Mobius transformations. And there's a nice theorem of Rivera-Letellier, who was studying dynamics of rational maps. If you iterate phi, it induces an iterated map on Berkovich space, and you can study things like the Fatou and Julia sets in that context. And one of the key things for trying to understand this action, which makes this Berkovich dynamics somehow simpler and gives you new tools to prove things about p-adic dynamics, the tool, one of the main tools is you can understand what happens to the path metric. So if phi is a non-zero rational function of degree d, then for all points in hyperbolic space, the distance from phi of x to phi of y is at most d times the distance from x to y. And this is proved, I'm not going to give a proof, but it's proved by proving something stronger, which is really just a local analytic fact, that if you look in the direction of some tangent vector v, then what's happening is that when you apply the rational function, it sort of stretches distances by a factor equal to the directional derivative of the map in that direction. So a rational map is sort of locally just stretching distances by some factor that depends on which direction you're moving in. And if you kind of globalize this and use some compactness argument, you get this theorem here. So you already see that derivatives of mappings in these tangent directions are important and interesting, and that will come up in our definition of harmonic function in lecture 3. So having discussed a little bit of that, and that's just some kind of introduction to maybe dynamics on Berkovich spaces, which I had originally thought about giving a lecture on, but I won't have time to do that. So that's just a little appetizer. So now I want to describe the structure of P1 Berk as a profinite R tree, some kind of inverse limit of finite trees. And this point of view seems to be useful for the kind of potential theory that I'll be doing in the next couple of lectures. And I think it's also a good way to think about the space, because this wild branching seems to get out of hand if you try to visualize this dense, countable, whatever, this wildly branching tree that I've drawn a small piece of for you. But if you think of it as an inverse limit of finite trees, it doesn't seem so bad. And in fact, that's the way to prove things, is to just reduce to the finite case and then take inverse limits. So here's a definition of an R tree. An R tree is just a metric space such that for each distinct pair of points, x, y, there's a unique path from x to y. And a finite R tree is one with finitely many branch points. So maybe I won't define precisely what that means, but intuitively, the idea is that this is just, you take a normal finite tree with finitely many vertices and edges, but you think of the edges as line segments having definite lengths. And so, for example, this Bruhat-Titz tree, which Jeremy was considering, he was thinking of the edges as line segments of length 1, right? And so that's an example. So that's called the geometric realization of this combinatorial tree. And that's an example of an infinite R tree, which was locally finite. A profinite R tree will be an inverse limit of finite R trees with respect to some inverse system. And I want to talk about the notion of a finite subgraph of Berkovich projective line. And so intuitively, this is just you take finitely many points corresponding to disks, and you draw their convex hull. You take all paths between them, and this is some finite tree in Berkovich space, which has finite length under the path metric. So officially, if I have any subset of this Berkovich projective line, I can take the smallest path-connected subset containing all the points of S. And a finite subgraph will mean the convex hull of a finite set of points of type 2 or type 3. So just take a finite set of actual disks, possibly of irrational radius, and look at the finite subtree of this massive infinite tree that these define. Yes? Okay, so the question was whether it follows from the definition of a inverse limit of finite trees that the space you get is actually a tree. At least if the, I mean, I will specialize to the case later where the maps are all surjective. They're just retraction maps from a bigger tree to a smaller tree. And then it's definitely true that it inherits the structure of a tree. But I'm not 100% sure in general if that's still true. In any case, I define an R tree as actually having a metric on it, and you might, when you take the inverse limit, you might get points that are infinitely far away. So officially, it's not, it doesn't have a metric on it anymore. So it's not an R tree in that sense that I define, but it still obviously has some sort of tree structure. Continuous maps, but in the application that I'll give in lecture 4, they will be retraction maps from a bigger tree onto a smaller tree.
But vertices go to vertices.
Well, our trees don't really have marked vertices and edges. Every point is a vertex. So you just define that they're continuous with respect to the metric topology. But yes, you should imagine that you can take some combinatorial model and vertices are mapping to vertices. And so this is just a loose term right now, which we'll need more axioms to make this a usable notion. I just wanted to be able to talk in general about this inverse limits. So by construction, a finite subgraph is finitely branched and has finite total length with respect to the path metric. And the collection of all finite subgraphs forms a directed system under inclusion. So you can have one, you take a finite subtree, the convex hull of a finite set of points, and then you add more points and you'll get a bigger tree. And you get a directed system. But you also can form an inverse system, namely, if one graph is contained in another, then there's going to be a retraction map from the bigger graph, from the bigger tree onto the smaller tree. And so you can also think of an inverse system under these retraction maps. So you just contract the points of gamma prime that are not in gamma to the point where they're sort of attached to gamma. And the theorem that's important in this context is that the Berkovich projective line is homeomorphic to the inverse limit over all finite subgraphs. So it's a particular example of a profinite R tree, but with very specific sort of retraction maps. So the content there, first of all, the content is that this map is a bijection from P1 Berk to the inverse limit. I mean, you see that the whole Berkovich projective line retracts onto any finite subgraph just by this kind of picture that I drew. And that map is continuous with respect to the Berkovich topology, which follows from the description of this observer's topology that I gave. And so you get a map to the inverse limit. And first of all, this is a bijection. And second of all, well, it's a homeomorphism with respect to the underlying topologies. And so I'll say a little bit more about this later, but I think this is a useful way to think about P1 Berk and its topology. And if you consider the direct limit of the graphs, then you'll sort of fill up this HR Berk, the set of points of type 2 and type 3. And with respect to suitable topology, that's a homeomorphism as well. So at least theoretically, you can think of the real points of this Berkovich hyperbolic space as the direct limit. And that's a much stronger topology. So this description sort of is actually useful for visualizing the Berkovich topology. So 2 points are close in Berkovich space if they retract to the same point on some large finite subgraph, or maybe more generally, if they retract to nearby points on a large finite graph. And first of all, I mean, you can see why P1 Berk is compact from this description, because it's an inverse limit of compact Hausdorff spaces, so it's going to be compact by Tikhonov's theorem. However, I guess the most convenient way to prove the theorem that these 2 spaces are homeomorphic is to actually use that they're both compact. And so this is maybe a red herring here. But oh, and I wanted to say that somehow I think of this, the homeomorphism with this inverse limit, it's in a way encoding Berkovich's classification theorem. Because you see, if you have a nested chain of disks, you can think of that as giving you a compatible family of points with respect to larger and larger subgraphs, where you take those points to be the endpoint of a growing tree. And so this nested sequence of closed disks is going to give you in the limit, it'll give you a point of the inverse limit. It'll give you a compatible family of points. And conversely, a point of the inverse limit, it's a family of points that retracts to the previous point under these retraction maps. And at least if you're moving downward in the tree, that will give you a nested sequence of disks. Of course, you can also move upward in the tree and have compatible families. But anyway, that's taken care of. I mean, so in fact, this is why Berkovich's classification theorem is not so useful to work with, because these nested families of disks, well, if you apply Mobius transformations, for example, I mean, they might go to disks around infinity. They become increasing families of disks. I mean, it's not, you have to, it's somehow an awkward notion to work with disks in A1 when you want to work in P1. And so actually this inverse limit construction takes care of all these ambiguities for you. You just have compatible systems of points. I mean, I'm trying to avoid saying sequence here because our indexing set might be very, very large. So we should talk about nets rather than sequences. Okay, so a simple domain you may recall was a sort of finite intersection of these Berkovich open disks. But you can see this very easily from this inverse limit description. So there's some retraction map from the Berkovich projective line onto any finite subgraph. And the topology, basically by the definition of the inverse limit, is given by subsets of the form, is generated by subsets of the form R inverse of V, where V is some, say, connected open subset of a finite subgraph gamma, and then you look at all things that retract into that open set. And those are exactly the simple domains that I showed you before. So here's a picture of an annulus, an open annulus. Right, so we have here my finite subgraph is this segment, and my open set V is the open segment, so everything except for the 2 boundary points. And I'm looking at all points of Berkovich space that when you retract to this segment here, so you look at there's going to be a unique path from that point out there onto this segment. And if it retracts to the interior of the segment, it's in the simple domain, but the points that retract onto the boundary, onto one of the 2 boundary points, are not in the simple domain. And so that is what I was calling before a Berkovich open annulus, an intersection of 2 open Berkovich disks. And you can actually see this is entirely compatible with Jeremy Teitelbaum's description of what was happening when you look at the edges, the open edges of the Bruhat-Titz tree, right? And he was saying that the set of all things for which this reduction map is an open edge of the Bruhat-Titz tree was an open annulus. So this is the same fact. And so for a subset U of P1 Berk, the following are equivalent. 1, U is a simple domain. 2, U is a finite intersection of Berkovich open disks. And 3, U is a connected open set whose boundary is a finite subset of H Berk R, the set of type 2 and type 3 points. So I guess what I had in mind here was that the definition of 1 was from the previous slide, the inverse image, this R gamma inverse of V. So those things are just the same as finite intersections of open disks, which is the same as any connected open set whose boundary is a finite set of points. Brian? Just the topological boundary. In the Berkovich topology. So in that case of the open annulus, those 2 points that look like the boundary are the 2 boundary points. So a simple domain has a finite set of boundary points, and as I mentioned, a finite set of preferred tangent vectors at those boundary points pointing inward. Okay, so again, this is a bit of a hodgepodge, just various things that I had wanted to say in lecture 1 and didn't have time for. So I want to talk about some more general constructions now, get away from just discussing the Berkovich projective line. And so I want to discuss the notion of a normed ring. So you can imagine the definitions from what various speakers have already said. If I have a ring A, these are commutative rings with 1. It's a function, a non-negative real-valued function, so that for every f and g, we have these obvious axioms here. And notice that I'm just requiring submultiplicativity for the norm, not multiplicativity. And it's not a semi-norm, it's a norm. So absolute value of f is 0, well, if and only if f is 0. So those are the axioms for a norm. A normed ring is a pair consisting of a ring and a norm. And, whoops, it's a Banach ring if A is complete with respect to this norm. And then a bounded multiplicative semi-norm on a normed ring, so bounded will refer to the given norm, is a function which satisfies roughly the same axioms, but it's a multiplicative semi-norm, so it's required to satisfy this stronger condition S3 of multiplicativity. And it has the boundedness property that the multiplicative semi-norm is bounded by some constant c times the given norm. And actually, you could take this constant c to be 1 by multiplicativity and taking nth powers and then nth roots, but that's a little exercise. And so the Berkovich spectrum of a normed ring as a topological space is as follows. So as a set, it consists of all bounded multiplicative semi-norms. And the Berkovich topology is the weakest one for which these functions are continuous. So this is very similar to the definition I gave last time, except there I was requiring that the absolute value on this polynomial ring extend the given one on k, and here there is no k, so we're replacing this by a boundedness condition. And these are necessary to guarantee compactness of the space. You can't just look at all multiplicative semi-norms, you need some auxiliary condition. And again, just concretely, this weakest topology for which blah happens concretely means that a fundamental system of open neighborhoods looks like this. And so a theorem of Berkovich is that if A is a Banach ring, then the spectrum is a non-empty compact Hausdorff space. So this is a very, very general construction to get a compact Hausdorff space out of any complete normed ring. And as a particular example of sort of how general this construction is, I want to consider the space M of Z associated to the Banach ring Z with its usual absolute value. And we'll give a picture of what this space actually looks like. By the way, I should say that for me anyway, the hard part of this theorem is the non-emptiness. Now, if the given norm is multiplicative, then obviously it's non-empty because you already started with a point in the space. But in general, there's some tricks that Berkovich uses in his book to prove that this space is non-empty. And then compact and Hausdorff are not as difficult. Okay, so in order to understand M of Z, what are we trying to do? We're trying to classify multiplicative semi-norms on Z, which are bounded with respect to the usual absolute value. And this is closely related to classifying all absolute values on Q. So recall Ostrowski's theorem, which gives this classification. So famous result in algebraic number theory, every non-trivial absolute value on Q is equivalent to either the usual absolute value or to the standard p-adic absolute value for some prime number p. And I'm normalizing so that the absolute value of p is 1 over p. And now this is classifying non-trivial absolute values up to equivalence. And we are actually considering all, not just absolute values, but multiplicative semi-norms. And we're working with Z instead of Q because if we're going to allow semi-norms, things that have a kernel on Z, they won't automatically extend to the field of fractions. So it's better when you're looking at semi-norms to concentrate on Z rather than Q. If you're looking at norms, then sort of equivalent to look at Z or Q. But multiplicative, and absolute values are multiplicative norms. So by multiplicativity, you can extend to the field of fractions. So if M sub Q denotes the set of places, that is equivalence classes of non-trivial absolute values on Q, then M sub Q corresponds to the set of prime numbers P plus infinity. And following Berkovich, here's how you classify multiplicative semi-norms on Z. So you've got Archimedean absolute values, which I'll write infinity comma epsilon, just taking the epsilon power of the usual absolute value. And that makes sense for epsilon between 0 and 1. As soon as epsilon is bigger than 1, you will fail to satisfy the triangle inequality. So you don't actually get a semi-norm. The p-adic absolute values make sense for epsilon between 0 and infinity because you have the ultrametric inequality. So now when you take arbitrary positive real powers of the absolute value, it still satisfies the ultrametric inequality. And you've got, of course, the trivial absolute value, which is 1 if you're not 0 and 0 if you're 0. And you've got these p-trivial multiplicative semi-norms. These are maybe the ones that you wouldn't have thought of before, which are 0 if p divides n and 1 if p does not divide n. And this is easily verified to be a multiplicative semi-norm, but note this has a non-trivial kernel, unlike these. These are all actually norms, multiplicative norms, but this is just a semi-norm. So these are kind of the analog of the type 1 points, actually. But here's a picture. So you get a path-connected, uniquely path-connected space. The infinite absolute value is here, and these are the epsilon powers of that for epsilon between 0 and 1. And then for each prime p, you get a branch. And you have the standard absolute values are sort of here. And then different choices of the absolute value of p will give you other points here. And these p-trivial semi-norms lie on the end. And really, this is the right way to visualize this space. And what is the topology? these segments are actually homeomorphic to segments, to real segments. And the topology in this point is such that an open neighborhood has to contain all but finitely many complete segments. So the open neighborhoods of this point are very large. For all but finitely many primes p, they have to contain this entire branch. And that is easily checked, makes it into a compact space. And it's also easily checked that this agrees with this abstract definition as the weakest topology such that blah, blah, blah is true. So very concretely, you can see what the topology is. And note that the tangent directions emanating from this trivial point are in one-to-one correspondence with the places of Q. So even though here we weren't dealing with equivalence classes, we were just treating every distinct norm as a different point, we can sort of recover the places of Q as tangent directions. And this will fit in well with the various descriptions that I'll be giving of how you should think of these tangent directions. So tangent directions at this trivial point correspond to places of Q. And, okay, so I already said what the topology on M of z is. We can metrize M of z in, well, at least once we've chosen representatives for these normalized absolute values, then we get a metric. So we can identify the branch going up, this branch here, we identify with the segment from 0 to 1. And these we identify with the segment from 0 to infinity. We attach a point at infinity. So we just think of those as segments parameterized by this parameter epsilon. And now we sort of have a metric space. We can measure the distance between 2 points. Well, so the endpoints down at the bottom are infinitely far away, but if you let hz be the complement of these points of type p infinity, you actually get a finite metric. And again, the metric topology is not the same as the subspace topology, as you can obviously see from the description that I just gave of what the Berkovich topology looks like. Now, the points of distance 1 from the trivial seminorm are exactly the standard absolute values, just by definition. So you can think of these standard absolute values with these, absolute value p is 1 over p. Those are the things at distance 1 from the center. And these points p infinity should be thought of as some kind of ideal boundary points that lie infinitely far away. And if you like, you can think of this as an inverse limit of finite R trees, exactly as before. So you just exhaust the space by bigger and bigger trees, finite trees of finite length that kind of go out towards these ideal boundary points. And you'll get those ideal boundary points just as limits of ends of these finite trees. So when you take the inverse limit over finite trees, you automatically get these ideal boundary points thrown in. So in that way, you can view this as an inverse limit, and it has the right topology. This topology I just described around the trivial point is captured by the inverse limit. So I think this is somehow the way to visualize this space, that you've got these metrized segments where from the trivial point to the epsilon, infinity to the epsilon has length epsilon. These to the standard absolute value has length 1, and these points here are infinitely far away. All right, so this metric will be very important in the next lecture when I define harmonic functions. There'll be some kind of general notion of harmonic functions, which depends on having an underlying metric. So I'll use that path distance rho for P1, and I'll use this metric for M of z to talk about harmonic functions. And in the last lecture, I'll talk about more general Berkovich curves and what the metric is there, and that's a slightly more subtle thing. And just to very quickly sort of wrap things up, I still haven't talked about many general spaces, so I just want to say what you can do without saying how you do it. You can associate in a functorial way to every algebraic variety x over k, or more generally to every quasi-separated, quasi-compact rigid space, some Berkovich analytic space. And I wrote locally ring topological space, but in fact, so you really should think of it not as a locally ringed space, but as a space with a different sort of structure, having a quasi-net or aphanoid atlas on it, and hopefully Brian will talk about this. So this is, but for algebraic varieties, it's not so much a loss of generality to think of the Berkovich space as a locally ringed space. And in the affine case, if for an affine variety, you can just think of the multiplicative seminorms on the ring A, which extend the given absolute value on K, equipped with this same topology we've been dealing with. And it's a non-trivial fact that this is compatible with the corresponding definition on aphanoids that Brian will be talking about. So for a rigid aphanoid space, you can also Berkovich analytify that. And these constructions are all compatible. And in particular, for A1 or P1, you recover the definitions that I've given so far. But it's much more general. And just in this generality, you get a locally compact Hausdorff space. If X is a proper algebraic variety, then the Berkovichification will be compact. And if X is connected in the Zariski topology, then you'll get a path-connected analytic space. And you get a canonical embedding of the k-valued points of X with this totally disconnected topology that Jeremy has pointed out we shouldn't completely diss. But you get that as a dense subspace of the Berkovich space. So all these things I've said work in general. And a theorem of Berkovich says, it's somehow much more general than this, but it implies that if you take a smooth projective variety over K, then the associated space you can think of as it admits a deformation retraction onto some finite polyhedral complex, which has some canonical piecewise linear affine structure. But this is related to resolution of singularities, and it's a very hard theorem. And I won't say anything more about that, except that in the case of curves, if you analytify a smooth projective curve, then what this means basically is that you have some deformation retraction onto a finite, canonically metrized graph. So a finite graph, but where the edges are thought of as having definite lengths, which we'll call the skeleton. And if X has good reduction, then the skeleton is just a point, and the whole space is contractible. So varieties with good reductions are contractible, but in general, the bad reduction will give you some kind of finite polyhedral complex onto which the whole space retracts. So that's the general picture of what happens with these Berkovich spaces, but here's the example of a Tate curve. An elliptic curve with multiplicative reduction you can think of as a circle of length log absolute value 1 over q, where q is the Tate parameter, this uniformizing parameter. You have a circle with some definite length and a bunch of trees hanging off it. So it's almost, and these trees have locally look like open aphanoids in the Berkovich projective line, open annuli, I guess. So you somehow can think of, it just looks like the Berkovich projective line, except instead of the Gauss point, you've drawn a big circle here. And again, this visionary French writer has already, way before Berkovich, discovered the analytification of Tate curves. Actually, I guess this looks like a sphere, so maybe it's the analytification of a K3 surface rather than a Tate curve. I'm not sure what Exupéry had in mind. And finally, here's a tree that's not simply connected. So here's the finite homology, and the rest of the space is just a tree. But it's allowed to have this finite graph with some homology in it. So thanks very much. Yes. So the dimension right, will be the same, or at least bounded by the dimension of the variety, right? Oh, okay. Is the simplicial complex, is the dimension related to the dimension of the variety? The answer is yes.
So your Berkovich space associated with Z, if you inverted P, would that just be pruning the branch corresponding to P?
Question is, if you take the localization of Z at P,
No, invert P.
Invert P and Z.
invert P and Z, what do you get? Yeah, I think it's pruning the tree, right? Cutting off that branch.
Is there a relationship with polyhedral complexes? Is that tied in with tropical geometry?
The question is the relation to polyhedral complexes tied in with tropical geometry? Yes, there's a paper by Gubler, a recent paper that discusses relations with tropical geometry. Where it comes from, and I'll discuss this in the last lecture, is the reduction. It's related to the structure of the special fiber of some nice model for your variety. So if you have good reduction, then you have some model which, with irreducible special fiber. As soon as you have more than one component, you can form some kind of reduction complex if the things at least have transverse normal crossings. And so for curves, if you take a semi-stable model, you'll have a reduction graph, a dual graph associated to the special fiber, and that topological graph will embed inside the Berkovich space, and everything will retract onto that. So it's closely connected with the type of reduction that you have.